All right, 2.4b has some friction problems. I have two kinetic and two static problems. I'm going to get right to it. These are meant to be a little tricky, and so we'll go through them. And please ask questions in class for anything you don't understand. So here's the first problem. This is a kinetic friction problem. There is an applied force on it. We always want to start with a free body diagram so we can see all the forces. They get especially important when you get into friction. So there's an applied force. It's 20 newtons. I'm going to call it F. If it's pushed horizontally in the positive x direction, then in the negative x direction, we have kinetic friction. I drew those arrows at different lengths. Ignore that. We have a normal force, and then we have the force of gravity. So this is a fairly common diagram for kinetic friction. There does not need to be this applied force in order for there to be kinetic friction. Something can be sliding along a rough surface with no force propelling it. Our job is to calculate the coefficient of kinetic friction. For now, here's my recommendation for setting up these types of problems. You have forces in two directions. I want you to set up net force in two directions. I want you to also set up the friction equation. Now this is kinetic friction, so Fk equals mu k times Fn. If you are going to find the force of kinetic friction, you are probably going to need all three of these equations, unless you're doing it in a multiple choice format, in which case you can mentally use them without writing them down. I'm going to go through every equation and we're going to see in what order we can solve things, and I'm going to start with the x direction. The x direction does have an acceleration, and it has a mass, and we have our 20 Newton force. So I'm going to rewrite this. The net force in the x direction is going to be F minus F sub k, and that's equal to mass times the acceleration. I have values for that applied force. It's 20 newtons. I have a value for the mass. It is 2.5 kilograms, and a value for acceleration. It's 1.8 meters per second squared. As it turns out, I can actually solve this equation, and when I do that, I get a kinetic friction force of 15.5 newtons. So that's really useful. That's like half the battle. I have now the force of kinetic friction. If I can find the normal force, then I can calculate the coefficient of kinetic friction. So this is a fairly simple problem because it starts out with everything you need to find the friction force in the direction of acceleration. Okay. In the y direction, well, if the acceleration is 1.8 meters per second in the positive x direction, then the net force in the y direction is going to be 0. Because once you establish the direction of acceleration, it makes the acceleration in the perpendicular axis 0. In other words, the block is not going to lift itself off the ground, or it's not going to burrow into the surface, and so there's no acceleration there. That means that the normal force minus the force of gravity is equal to 0. That means the normal force is equal to m times g, so that's 2.5 times 9.8, and the normal force is equal to 24.5 newtons. And that is the other half of the battle. So now we can plug into our friction equation. So 15.5 equals mu times 24.5. And when I divide that out, I get mu is equal to 0.63. So that's not an easy problem, but it's a straightforward problem. And in the order I wrote out the equations, that wound up being the order in which I solved the problem. All right, second problem. We have an inclined plane, and we're looking for the acceleration if I know the coefficient of kinetic friction. So I'm going to, again, set up the free body diagram. Now the incline is going to go that way. So I'll have gravity, and gravity's angle is going to be there. We have a normal force in the perpendicular direction, and then we have kinetic friction in the parallel direction as a force of resistance. All right, so now I'm going to set up my three equations: the net force in the parallel direction, the net force in the perpendicular direction, and then the friction equation. Again, it's static friction, so I get to use the equal sign. All right, and then I try to solve things and see where I go. I'm going to skip some of the stuff that was covered in the previous parts of the unit, and if you need some help connecting these dots, let me know. The net force in the parallel direction is going to result in an acceleration. Now there's two components. There's the component of gravity that is parallel to the plane, and then there's friction. If I do my trig, I can rewrite this as mg sine theta minus the force of kinetic friction equals mass times acceleration. And I mean, I can plug some stuff in, but I don't have everything yet. So I can't finish this part of the equation because I don't know what the force of kinetic friction is, and I don't know what the acceleration is. So once I find the force of kinetic friction, then I can come back to this. So let's start a new line with the parallel net force. This should be equal to 0 for reasons we stated above in the first problem. There's no acceleration perpendicular to the plane. It's just going to slide down the plane. This means that the normal force minus mg cosine theta is equal to 0. So this is something I can calculate. The normal force is going to be 0.8 times 9.8 times the cosine of 25 degrees. Normal force is a value that I can get. It's 7.1. I'm going to keep a couple extra decimal places, 7.105 newtons. So this ended up being the first thing that I did. I found the normal force. With the normal force and the coefficient of friction, I can get the friction force next. So this is a simple calculation. The friction force is going to be 0.25 times 7.105. And so the force of kinetic friction is 1.776 newtons. So I just used the perpendicular direction and the definition of kinetic friction to find that. And now I go all the way back to this first equation and I fill it in. I know I'm not going to have enough room to write all of that in this column I've made for myself, so I'm going to make a bigger section here. I'm going to fill in everything I have. So the mass is 0.8, g is 9.8 times the sine of 25 minus 1.776 equals 0.8 times acceleration. Okay, so I had to go and do stuff in other equations first because I needed to have the friction force in order to find the acceleration. But once I do that, I can plug all that in, and I get an acceleration of 1.9 meters per second squared. I have two more problems to go through. I know this video is getting on the long side, but I'm going to push through. You can always take a break and come back to this later. The static friction questions are different, and for obvious reasons. Static friction works differently. Describe the behavior of this box sitting on a flat, rough surface where you know the coefficient of kinetic friction during the following horizontal forces. So I'm going to draw a free body diagram. That free body diagram involves gravity, normal force, an applied force, and a friction force. And I have to analyze this with all of these forces. Now, there's a trick to this. What I know about static friction is that there's a certain threshold. So I want to focus on the maximum static friction force, and that's going to be equal to mu times the normal force. So I'm actually just going to evaluate that equation and then make my conclusions. I need to know the normal force. So what we've been doing so far is saying that the net force in the y direction is 0 and that the normal force is equal to the weight, which is going to be 3 times 9.8, which is going to be 29.4 newtons. So I can find the normal force in this box. It's under the same vertical conditions each time. I can then apply that to the maximum static friction force. That's equal to 0.85 times 29.4 newtons. And so this maximum static friction force is equal to 25 newtons. Okay. And that's all I need to know. Any applied force under 25 newtons and nothing will happen. So for an applied force of 10 newtons, there is no motion or no change in motion. For an applied force of 20 newtons, there is no motion because those applied forces are not strong enough to overcome static friction. However, an applied force of 30 newtons does create a net force, and you do get acceleration from that. If you needed to determine the acceleration, you'd actually need to know about kinetic friction at this point in time. But for now, we just want to say, okay, well, only under this circumstance will the object start to move. All right, last problem is about a car. And so we have to talk a little bit about this. This is talking about static friction between a car's tires and dry road. And so I'm going to draw the tire and I'm going to draw the road. Now, let's say the car is going to move to the right. And so that means that the wheels are going to be turning from our perspective in the clockwise direction. What that means is when the part of the tire that's going to touch the road gets to the road, the tire's bottom section is moving to the left. That means that the bottom of the tire is pushing the road to the left. That means that the road is pushing the tire to the right. And that is why the tire moves to the right. So because the tire is rotating in this direction, when we think about what's happening at the bottom of the tire is always moving to the left, which means it can only push things to the left. It pushes the road to the left, the road pushes the tire to the right. So when we go to draw a free body diagram, we have mg, we have Fn, and we have this static friction force pointing to the right. That is the only reason why the car moves, is because static friction from the road is pushing it forward. Our job is to find the maximum acceleration, so we're going to do the same thing we've always done. Set up three equations. Net force in the x direction, net force in the y direction. I know that's 0, so I'm just going to start there. And then static friction force. This is going to need to be the maximum static friction force because I want to know the maximum acceleration. So basically, like, how hard can I push down on the gas and still have the car accelerate without spinning out? If I push harder on the gas, the tires would spin out. I'd have kinetic friction, and I would not have as big an acceleration. And so I'm going to follow each of these. In the x direction, I just have static friction force that's equal to mass times acceleration. That equation is a dead end because I don't have any of those variables. I don't have knowledge of any of those variables right now. So I move to the y direction. The y direction is kind of the usual. Normal force equals mg. I don't have any way to calculate that because I don't know the mass of the car or the car's tires or anything. So I start to do substitutions. The maximum friction force is equal to mu times the normal force. Well, if the normal force is equal to mg, then the friction force is equal to mu times mg. Mu times mg is going to come up here and there for us, having to do with friction. So mu mg is the magnitude of the static friction force. So I've performed a substitution. The normal force equals mg. That tells me what the static friction force is equal to. And now I can add what I know the static friction force to be into my second law equation. What I'm left with is mu mg equals mass times acceleration. And I get a lot of good news here because the masses cancel. So both terms in this equation have m, and I am left with 1.05 times 9.8 equals the acceleration. And so the acceleration is 10.3 meters per second squared. So that's the maximum acceleration that car could have without spinning its tires based on that coefficient of friction. So like uh, people who make tires for NASCAR, or companies that make tires for NASCAR, they build them so that they have the maximum force of friction available to them, and the mechanics who work on the cars actually deflate the tires a little bit so that they get more grip, to get more of a coefficient of static friction. That's it.